In the previous lecture, we have derived the Jacobi method for finding the eigenvalues and the corresponding eigenvectors of a symmetric matrix. However, there is a disadvantage in the method, and that is a 0 that has been created can be destroyed in the later rotations. Therefore, we are not sure of the number of rotations that a particular problem would take. Therefore, except if there is no alternative, we can use that particular method. However, we have some alternative methods which would see that the zeros that have been created once, they are retained as zeros. That means, zeros created once, they are not destroyed. One such method is known as the Givens method. So, let us describe the Givens method for symmetric matrices. Now, the method is derived in 3 steps. The method does not reduce the system A to one of the known 3 forms we have. We have a matrix as D, L or U, that is diagonal, lower or upper triangular, but this method reduces a matrix to a tridiagonal form. That means, one main diagonal, one super diagonal and one sub diagonal. So, the first step is reduce a matrix A, reduce A to a tridiagonal form. So, we will now reduce the given matrix to the tridiagonal form to this by using the plane rotations. The transformations we are using the same as in the Jacobi method by using plane rotations. Then in step 2, we will form the Sturm sequence for finding the characteristic equation of this matrix. So, if the given the new matrix is B, if I call this as matrix B, I will find out the characteristic equation of this matrix as B minus lambda I and denote it by f n suffix n for the order of the matrix n. So, this is the characteristic equation of the matrix B. Now, in step 2, I will now form a Sturm sequence to find this characteristic equation. So, form a Sturm sequence, to find a sequence to find a sequence which approaches f n. That means, we are going to derive a sequence f naught, f 2, so on, and the last member of this sequence is our characteristic equation. When once it is a Sturm sequence, I can find the number of changes in sign in any interval a b and then determine the number of eigenvalues that are there in the interval a b. Now, you study the changes in sign, the number of changes in sign in the sequence and locate the eigenvalues. When once we locate the eigenvalues in a particular interval, everything is now dependent only on the change in signs of this sequence. Therefore, I can use the bisection method to reduce the interval further and further and get the required accuracy, because we are now using only the signs. Now, therefore, bisection method is used, bisection method can be used to refine these intervals. Therefore, we can obtain the eigenvalue to required accuracy, whether you give the 4 plus 5 plus 6 plus accuracy. I can get the accuracy of these eigenvalues by go on bisecting the interval in which the eigenvalue lies in. So, it is just by changing the looking at the number of changes in sign in this term sequence. And the third step is to find the eigenvectors. Step 3 is find the eigenvectors. Find the eigenvectors. Now, let us go back to the step 1 and see how we are going to achieve this tridiagonal form. Now, we are using the same orthogonal matrix as we have done in Jacobi. So, we use the same orthogonal matrix that was cos theta minus sin theta cos theta to reduce A to tridiagonal form. Now, the most important thing here is that we always start from 2-3 submatrix, that is A22, A23, A32, A32. So, it is always we concentrate on 2-3 submatrix. We always start with the 2-3 submatrix. That means, our locations A22, A23, A32, A33. Of course, A23 is equal to A32, we are the symmetric matrix. That means, we are now starting with this location, these two locations 2, 3 and 3, 2. We are not touching the first row, we are not touching the first column. Then I perform the rotation, and then in Jacobi we set these two elements as 0, finding the off diagonal largest off diagonal element and then making this as 0, and then we are determining theta. But here we will not do that, we perform the same rotation as we have done in Jacobi, but we find theta and set this element above as 0. That means, we set the element A13 as 0, not this the element as 0, but we set the above element as 0. Now, perform rotation, find theta such that, let us call the mu matrix as A prime. So, A prime 1 3 is equal to 0. That means, it is just above this element over here. Now, let us see what this gives us. So, the transformation would be, let us call it, we will call this as A prime I j, the new matrix, as S1 inverse A S1, it is orthogonal. So, S1 transpose A S1. And in this new matrix we are saying that set A prime 1 3 is equal to 0, that is what we are saying. Now, let us write down this matrix A1. The first row is not changed, so it retains as it is, as 0 cos theta, and this is transpose of it. Therefore, I will have a sin theta over here, 0 minus sin theta cos theta. So, I inserted the matrix in the 2 3 sub matrix position 2 2 2 3 3 2 3 3. Then I will write down our matrix A 1 1, A 1 2, A 1 3, A 2 1, A 2 2, A 2 3, A 3 1, A 3 2, A 3 3, and I do not need these elements. So, I will just retain the elements as it is. Then I have again 1 0 0 0 cos theta minus sin theta 0 sin theta cos theta. These are all zeros, we have all zeros. Here also we have all zeros. Now, let us retain this matrix as it is and let us write down this product. So, because this is 1 0 0, the first column remains as it is A 3 1, it remains as it is. Then let us go to first row second column. This is A 1 2 cos theta plus A 1 3 sin theta, A 1 2 cos theta plus A 1 3 sin theta. The first row third column gives minus A 1 2 sin theta plus A 1 3 cos theta. Now, I need these two elements also. This is A 2 2 cos theta, A 2 3 sin theta, this is minus A 2 2 sin theta plus A 2 3 cos theta, and similarly A 3 2 cos theta, A 3 3 sin theta minus A 3 2 sin theta plus A 3 3 cos theta. Now, in this product I want to set 1 3 location as 0. So, I will now write down in this product only A 1 3 location and corresponding symmetry, therefore, both the locations are the same. So, let us write down the location, the third location from here. So, this will give me some element here, some element here. Now, 1 is multiplying this. So, it will simply give me minus A 1 2 sin theta plus A 1 3 cos theta. So, first row I am multiplying the first row is simply 1 0 0. So, I am multiplying this with this one. Now, I would, if you look at this third element here, again I will have here minus A 1 2 or A 2 1 sin theta plus A 3 1 cos theta. We do not need any other elements, we need only this element, because of symmetry we know these two locations are same, A 1 3 location, 3 1 location will identically be same. Now, I want to set this element as 0, therefore, I will set A prime 1 3, this is our prime matrix, this we are calling it as A prime I j. So, A prime 1 3 is 0 will give minus A 1 2 sin theta plus A 1 3 cos theta. Therefore, this gives me tan of theta is equal to A 1 3 by A 1 2. This value of theta produces zeros in the location 1 3 and 3 1. So, this rotation produces zeros in 1 3 and 3 1 locations. Now, we would like to move along this row. The first step we are doing the rotation in the submatrix system 2 3 system. Now, what we do is I now move to the 2 4 subsystem. 2 4 means 2 4 4 2 4 4. So, we move along the row to the right. So, we can say now move to the right along the second row. What we mean by this is, therefore, it means we consider 2 4, when after we complete 2 4 we go to 2 5, after we complete 2 5 I will go to 2 n, the entire row. So, we move along the row each one, but with the pivot of course is 2 4, 2 5, 2 3, 2 n and so on. So, we move along this particular row, and every time we set the find the value of theta such that the element, as we have done here, the element above this is 0. So, when I go to the next element here 2 4 subsystem, then I will now make this as 0. That means, let us just write what it is. Now, this first row stands as it is, the first column stands as it is. Now, I will have 2 and 4. So, this is a, we do not consider this, we do not consider this, then I consider this, I will consider this. This is our 2 2 location, this is your 2 4 location, your 4 2 location and 4 4 location. So, I would consider these 4 elements and then make this element as 0, the value of theta that is determined by setting this as 0. So, on in the final stage I would have this column, this 2 2 element, and then I go to 2 n element. This is 2 n, this is 2 2, and I now have here n 2 element and n n element. I will now set last element as 0. Now, in each rotation find theta by setting the element above a to j as 0, where j is equal to your, now we have taken it as 4, 5 and so on n. So, in each rotation we find theta by setting the element above, that is the location 2 j as 0, for j is equal to 4, 5, 6 and so on n. Now, what happens is, in each time when we are setting this this, the value of tan theta would be same, that is your element a 1 4 by a 1 2. This a is not the original a, the new a in the rotation, these are all new a's in the rotations. We have performed the first rotation, then we are calling the matrix again as a elements. So, you are using with the new a's. So, in the next step it will be tan theta will be a 1 5 by a 1 2 and so on, and lastly we will have tan theta is a 1 n by a 1 2. If I perform this rotation, then what we have done here is, we have produced now, we have left the first 2 elements, then we made these all these elements as 0, the element above has been made all of them 0, and then here the elements below also have been made as 0, because correspondingly symmetry. Now, all these elements are now available to you, these are all non-zero elements. This is the what we have done in this step. Now, we move down, but to the third pivot. Now, we started with the pivot 2 2, now I go down to third pivot, that is your, we start with 3 4, therefore, I will start with 3 4, 4 3 4 4, again set the element above as 0. Therefore, every time we move down a row, then find theta such that the element above is 0. So, we will now move down 1 row, move down by 1 row. Now, consider the sub matrices in 3 4, then 3 5, so on 3 n locations. That means, we are considering when we are talking of 3 4, we are talking of your third pivot 3 3 pivot, this is your 3 4 and this is your 4 3 and this is our 3 3 location, 3 4 location, 4 3 location, 4 4 location. Set the element above this as 0 and find theta. So, find theta by setting the element above 3 j, that is j is equal to 4 5 so on n to 0. Find theta by setting the element above this 3 j element, that is 3 4 or 3 5 3 n to 0. Then this will give us zeros in the second row starting from the fourth element and correspondingly this one. Finally, move to n minus 1th row and perform the rotation. Move to n minus 1th row and perform rotation. If I do this, then the matrix has been reduced to element here, we have now made all these as zeros, element here, all these have been made zeros. So, what I would therefore have is element here, we will have an element here, element here, element here. Which is nothing but the tridiagonal system. So, this is reduced to a tridiagonal form. Now, the number of rotations we can count here, there are n minus 2 to be set in the first row, n minus 3 in the second row and 1 here. Therefore, the total number of rotations is n minus 2 plus n minus 3 so on plus 1. Therefore, this is n minus 2 into n minus 1 by 2. Now, this is the exact number because 0 that is created once, 0 that is created is not destroyed. That means 0 1, once we create 0 it remains 0 right through the all through the rotations. Therefore, this will be the exact number of rotations. So, we are able to say that I need exactly n minus 2 into n minus 1 by 2 rotations to bring a matrix to a tridiagonal form. So, this is something very good because we are able to say exactly the number of rotations that is required and there is no option on a particular problem or it is dependent on a particular problem to have the number of rotations vary. Now, when once I have created this, so let us call this as a matrix B. So, I have now produced the tridiagonal system B1 C1 symmetric, therefore, this must be C1, this is B2 C2. So, it will be C2 B2 B3 C3 and so on Bn, I will have this as Cn minus 1. So, the matrix is going to look like this. Now, these are similarity transformations which we have done, therefore, A and B has the same eigenvalues, have the same eigenvalues. Now, there is a theoretical observation on the eigenvalues of a tridiagonal matrix. What it states is, if all the off diagonal elements are not 0, then the eigenvalues of this are distinct. So, that is a property of the tridiagonal system. If C I is not equal to 0, then the eigenvalues are distinct. Then the eigenvalues are distinct. Now, you can see that if any one of them is 0, it actually degenerates into two systems. Let us set, suppose C 3 is 0. So, there is a C 3 here, therefore, there is a C 3 here. If I have C 3 as 0, this is 0, this is 0. Now, this does not contain anything belonging to this system, and this does not have this B 1 B 2 B 3 or C 1 C 2 C 3. Therefore, if any one of the C I is 0, then this system disintegrates into two subsystems. So, the eigenvalues of each smaller systems can be determined in that case. So, if C I is not equal to 0, then that does not happen. So, if any C I is equal to 0, then the system reduces to two lower order systems. Then the system reduces to two lower order systems. Now, forming the Sturm sequence from here is very simple. We will define our characteristic equation f n as determinant of either lambda I minus b or b minus lambda I. So, this will be lambda minus b 1 minus c 1 minus c 1 lambda minus b 2 minus c 2 then I will have minus C 2 lambda minus B 3 minus C 3. I will have this is lambda minus B n minus C n minus 1. This is the determinant, this is the determinant. This is our, you can set it equal to 0, that is our characteristic equation, but I want to have the Sturm sequence for f n. So, this is our characteristic equation. So, let us drop this 0 for the moment. I define expand this by minors, expand by minors. We define f 0 as 1. So, with that I take 1 into 1 minor, that is simply lambda minus b 1, denote that by f 1, that is lambda minus b 1. This is a 1 into 1 minor. Then I will take 2 by 2 minor, that is the determinant of these two, but I will always expand by the last row or last column. So, I will expand it by the last row. So, I will have lambda minus b 2 multiplied by lambda minus b 1, lambda minus b 1 is f 1. So, I will write lambda minus b 2 into f 1 minus c 1 square into 1. So, I will write this as f 2 as lambda minus b 2 into f 1 minus c 1 square f 0. I mean, if you just want to have a look at this one, this is what we are considering this. I am expanding it by the last row. So, lambda minus b 2 into lambda minus b 1, and that is your f 1 minus this location is minus 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 plus into this product, therefore, minus C 1 square always into 1. Now, this is your 2 into 2 minor. Now, I take the 3 into 3 minor, and that is lambda minus B 1 minus C 1 minus C 1 lambda minus B 2 minus C 2 minus C 2 lambda minus B 3. Now, this I will call this as F 3, this I will call it as F 3. Now, let us expand again by the third row, lambda minus B 3 into this determinant, which is already F 2. So, this is lambda minus B 3 into F 2. Then minus of minus, that is plus C 2, and we have removed this column and this row. So, I will have here minus C 2 into lambda minus B 1, that is F 1, that is minus, I have removed this particular column and this row. So, I am expanding the determinant. So, this will be minus C 2 into lambda minus B 1, lambda minus B 1 was F 1. So, this will be lambda minus B 3 F 2 minus C 2 squared F 1. Therefore, I have the general formula lambda minus B r F r minus 1 minus C r minus 1 square F r minus 2 for all values of r lying between 2 r and n. So, all of them can be written in a recurrence relation form. This is simple recurrence relation that will go. So, in the recurrence relation we can immediately compute all the values, and the last one f n is our characteristic equation. Therefore, f n is equal to 0 is the characteristic equation. Now, if none of these C i's are 0, which you have assumed earlier, then this sequence f 0, f 1, f 2, f n forms a Sturm sequence. This proof I will not take it, but I will give this result. If C I is not equal to 0, then f 0, f 1, f 2, f n forms a Sturm sequence. Now, I can choose an arbitrary interval, any interval a b. Let us suppose I take an interval a b, then I can study the, if f n is 0 at any one of the endpoints, obviously it is an eigenvalue. Otherwise, I can study the number of changes of sign of this Sturm sequence in the interval a b and then locate the eigenvalue in the interval a b, if it is there or it is not there. Therefore, study the changes in sign, study the changes in sign of f j and locate the eigenvalues. And locate the eigenvalues. Now, we shall use bisection to refine these eigenvalues to the required accuracy. Refine the eigenvalues, regarding the eigenvalues using bisection, obviously to the required accuracy. Now, if you just want to find the eigenvalues, the Gibbons method is the most powerful method, because the number of rotations are fixed and it works very fast, because it just changes of sign to be studied and it works very fast, and is one of the most powerful methods for finding the eigenvalues if you want to find eigenvalues alone. Now, let us see how do you find eigenvectors. Now, let us just remember what we have done. We started with our matrix Ax is equal to lambda x. Now, we perform these operations. So, what I do is I first pre multiply this by S inverse. So, I will have here S inverse Ax is equal to lambda S inverse, lambda is a constant. So, I take it out. Now, in order to bring your similarity transformation S inverse As, I will now set x is equal to some s into u. I will set x is equal to s into u. Then this will read S inverse A S u is lambda S inverse S of u. The left hand side is what we have finally obtained, B, that is your B of u is lambda of u. That means, the eigenvalues of A and B are same that we know, therefore, lambda is the eigenvalue of B. Now, u is the eigenvector of B. Now, therefore, we have lambda is an eigenvalue of B and u is the eigenvector of B. U is the eigenvector of B, but what is u? We can just look back here, u is equal to S inverse of x, u is equal to S inverse of x, or look at the other way around, x is equal to S of u. In other words, if I can find the eigenvector of the new matrix, tridiagonal matrix, then I can obtain the eigenvectors of the original matrix by simply pre multiplying by the matrix of transformation S, and that is S is equal to, as in the Jacobi method, this is simply SR. SR is equal to n into R is equal to n minus 2 into n minus 1 by 2. We have the exact number of rotations as this. So, which I will call this as R. So, S is equal to S1 S2 SR, and when once I determine this, I can now write down what is my S into u. Now, if now I have to find out what is the eigenvectors of B. The eigenvectors of B is very trivial, because you know it is a tridiagonal system. You can drop any equation in arbitrarily any equation in between, solve the system above, solve the system below, then it is by forward substitutions you will get the solution, and the eigenvector u will be having 0 in the location where you have neglected the equation. Suppose you have neglected ith equation, then we set 0 in the ith location, and the remaining elements of u will be the solution of the problem that we have done, because that is a straightforward solution of a problem. So, for finding u, the neglect any equation, in B u is equal to lambda u. So, that is what we have, B u is equal to lambda u, neglect any equation in this, solve the remaining, solve the remaining equations. So, if ith equation is neglected, then u is equal to the elements that we have got and 0 in the ith location and the elements that we have get over here. So, we put 0 in the ith location, that particular row that has been neglected, and the solution remaining part is the solution that we obtained, and that will be my u. Even once I find u, I know that x is equal to S into u. Therefore, this is a little bit extra computation in the Givens method if you want the eigenvectors also. Okay, let us first of all take an example on this one. Reduce the matrix that is 1 2 3 2 1 minus 1 3 minus 1 1 to tridiagonal form. Using Givens method. Now, we start with always 2 to submatrix. So, we start with 2 into 2 submatrix. That is your A22, A23, A32, A33. Now, tan theta is A13 by A12, A13 by A12, that is A13 is 2 and A12 is 2, that is 3 by 2. Now, let us do exact arithmetic so that we have the we do not have decimal numbers. So, let us write it let us write down secant square theta from here, that is 1 plus tan square theta, that is 13 by 4. Therefore, I can get cos theta from here as 2 upon root 13 and I can get sin theta as under root of 1 minus 4 upon 13. So, that is 3 by root 13. Therefore, the first rotation will give me first rotation. Indeed, here there is only one rotation that is required because we want the tridiagonal system. Therefore, I need the diagonal, I need one super diagonal, the sub diagonal. Therefore, there is only one element to be made 0 here. Therefore, there will be only one rotation, even though we have written first rotation, this is the only one. This is the only one rotation that we will have. What will be the matrix that we will have to write down? 1 0 0 0 cos theta, this is transpose. So, I will have here 3 by root 13, 0 minus 3 by root 13, 2 by root 13. This is your S transpose. Given matrix is 1 2 3 2 1 minus 1 3 minus 1 1. So, this is our matrix A. Then I will have S matrix 1 0 0 0 2 by root 13 minus 3 by root 13 0 3 by root 13 2 by root 13. Now, let us retain this matrix as it is and let us write down the product. So, we will have this is 1 0 0, the first row gives me this first row into this 1, it remains the same. Then this is 2 into 2 4 plus 9. So, 13 by root 13. So, I will have root 13, this is 4 plus 9. So, root 13. Then here this is minus 6 and this is plus 6. So, I will have a 0 here. This row, this column again 2 into 1 is 2. Then we are multiplying these two, this is plus 2, this is minus 3. So, we will have minus 1 by root 13. Then this row, this column, this is minus 3 minus 2, we will have minus 5 by root 13. then 3 remains as 3, then this is minus 2 plus 3, therefore, this is 1 upon root 13, this is plus 3 plus 2, that is plus 5 by root 13. Now, we are multiplying now the first row is remains the same, therefore, this 1 root 13 0 remains the same, because we are multiplying by 1 0 0. Now, the second row first column, that is 2 into 2 4, that is 3 into 3 9. So, 13 by root 13. So, I will have here root 13, then 2 into minus 1, that is minus 2 plus 3. So, I will have 1 by root 13, 1 by root. Yes, no root, yes, no root. Then I have this row, this column, this is minus 10 and this is plus 15. So, we will have here 5 by 13. Then this row, this column, this is minus 6 plus 6, this is 0. Of course, I can fill these elements, but let us see it, because it is symmetric. So, I can without computing I can write it, but let us see that we have done the problem correctly. So, if I multiply this and this, I will get here plus 3 plus 2, that is 5 by 13, and the last row gives me this is plus 15 plus 10. So, I will have here 25. Now, as I said that in actual practice, when you are doing we need not do this element, because we know it is symmetric, it has to come when once you find these elements, we can symmetrically write those elements, unless we have done some error in the problem, otherwise it will be the same. So, we really do not have to waste the time in evaluating the other elements also. Now, this is the problem that we have been asked to reduce into the tridiagonal form. So, we have this is the required tridiagonal form, which we obtained in one rotation. Now, the next step, if we want the eigenvalues, I will take a simpler example, because numbers look to be little complicated here. I will take a simpler example and then show how we can obtain the eigenvalues using this term sequence. We can get it, but since as I was saying the numbers are little bit complicated, we need decimals. So, we will take a separate example, then we will do it next time.